Now let's take a look at significant figures. And significant figures are the way that we correctly record measurements, and we write the number part of our measurements to reflect the precision of the instrument. So let's take a look at what we mean by precision. So if we look at these three numerical parts of a measurement, they are all taken to different place values. This is to the thousandth, this is to the 10,000th, this is to the 100th, and this is to the 10th. I think you can see that this is going to be the least precise measurement because we have a value only out to the tenths place, and then this right here is going to be the most precise. Now, if these numerical parts of the measurement are correctly recorded, then the last digit is what's known as the uncertain or the estimated digit. So let's look at more detail at that. When we write a measurement, the way we write it always indicates the precision of the instrument. The last digit is always an estimated or uncertain digit, and that digit, as well as the ones that we know for certain, are what are known as the significant figures. When a numerical measurement is written, all the digits written are known with certainty except for the last one, which is an estimate. Now, this is one area where chemistry deviates from math, and that is because in math all numbers are the same. And I actually said that badly. I didn't mean that all numbers were the same, but what I meant that was in math 2 is the same as 2.0 is the same as 2.00. However, in chemistry, these three values are very different if they are the numerical part of a measurement. This measurement here would have a different precision than this value up here. Whoops. This value here only has one digit, and so by definition that has to be the estimated one. Here this is our estimated digit, the 10th place, and here this is our estimated digit, the 100th place. So in math land, these three are equivalent, but in chemistry land, these are very, very different. These measurements would have come from different instruments. This would be the most precise, and this one would be the least precise. So in chemistry, we have two different types of numbers. We have exact numbers that have what we consider to be an infinite certainty, such as numbers that we get by counting. So for example, how many pennies are in a pile, how many apples in a basket, how many students in a classroom. And then numbers that are given by definition, such as pi, or the relationship between units, such as 1 ounce is exactly 1/16 of a pound. These are all considered to be exact. There's no uncertainty associated with them. However, measurements always have uncertainty. There's a limit to the certainty of any given instrument, and the way that a measurement is recorded indicates where that limit is. So let's take a look at a measuring device, and let's look at how to correctly record the data. When we are recording the numerical portion of data, the last digit and only the last digit is estimated. So we're going to take a look at this. I'm going to make this larger. I personally would never like to use this particular instrument in the lab because it's really not that precise. If we look at it, we're going to look at the metric side here, the gram side. I'm measuring the mass of this chemical. And here are 0 grams, here are 10 grams, and then each graduation in between is going to represent 1 gram. So if I look at this line, let's see if I can get a little bit bigger. It's a very thick line, and the distance between these two graduations is very small. But this line is definitely closer to the 1 gram mark than it is the 2 gram mark. So how do we correctly record this? The author of this slide wrote down 1.2, and I certainly agree that this has the correct number of digits. 1 is known for certain, and then this here is the estimated. I might be inclined to put a 3 there, but 1.2 or 1.3 would be the correct way to write it. The last digit is estimated, and anyone looking at this measurement would know that this is estimated and this is known for certain. So go ahead and pause this slide and see if you can correctly record the temperature on this thermometer. So what we want to do is we want to have one digit, the last digit, that is estimated. If we look at this, we know for certain that this is it's between 103 and 104, and it looks to be right about in the middle. I would be inclined to say 103.5 degrees Fahrenheit. This tells us that it's the Fahrenheit scale. But if you did 103.4 or just had one digit after the decimal point, you're in good shape. Now I think you would agree that it would not be 103.9 or 103.1, that this is somewhere right in the middle between 103 and 104. So 0.4 or 0.5 would be the correct way to express this. Okay, now let's look at this uncertain digit, this estimated digit, which is always last, and let's look at the range of precision. When we look at a measurement such as this one, 12.3, this has three significant figures. The last one is estimated. These two are known for certain. And it is assumed that this last digit is going to be plus or minus 1, meaning its range is going to be between 12.2 to 12.4. So our 3 is in the 10th place. So our range of precision is plus or minus 1/10. The actual measurement is going to be somewhere between 12.2 and 12.4. Let's look at this value, 12.30. This has a greater precision than this. This has 4 significant figures. Our 0 is our estimated digit, and the range of precision is plus or minus 1, the hundredths place. So here's our range of precision, plus or minus 0.01, because that's the place value of our estimated digit. So this measurement is more precise than this, and it has a range somewhere between 12.29 and 12.31.